We abandoned the moon, not because we had to, because we decided it wasn't worth it anymore. For reasons that, even 50 years later, don't quite add up. We moved on. We told ourselves the story was over, but it was never over. It was interrupted. And what interrupted it changes everything. And here is a question. If you could bring one person with you to the moon to keep you entertained for 1 year, who would it be? Let me know in the comments. I will pin the most creative answer. Now let's begin. To truly understand why we stopped going to the moon, you have to understand why we went in the first place, and the honest answer might surprise you. It had almost nothing to do with science. Think back to the late 1950s. The world had just come through the Second World War. The United States and the Soviet Union were locked in the most intense ideological standoff in human history, a Cold War that felt every single day like it could turn hot and end everything. Both sides had nuclear weapons, both sides had missiles, and both sides were terrified of what the other could do. Then, on the 4th of October 1957, something happened that changed everything. The Soviet Union launched a small metal ball into orbit around the Earth. It was called Sputnik. It was barely bigger than a beach ball. It beeped. That was it. It just beeped as it flew over your house. But that beep sent shockwaves through American society that are hard to overstate. Because if the Soviets could put a satellite into orbit, they could put a nuclear warhead anywhere on the planet. No warning, no defense, just a beep, and then nothing. The panic in Washington was immediate and overwhelming. Congress held emergency sessions. The media ran headlines about American vulnerability. President Eisenhower, a former five-star general who had commanded the largest military operation in history, publicly admitted that the United States had been caught off guard. And then, 4 years later, on the 5th of May, 1961, the Soviets did it again, this time far worse from America's perspective. A young cosmonaut named Yuri Gagarin became the first human being to leave the Earth and orbit our planet. He was 27 years old. He went into space, circled the globe in 108 minutes, and landed safely in a field in Russia. The Soviets had won the first chapter of the space race completely, and the humiliation in the United States was total. President John F. Kennedy knew something dramatic had to happen. He could not let the Soviet Union hold the high ground, literally. So on the 25th of May, 1961, he stood before a joint session of Congress and made one of the most ambitious promises any leader has ever made in the history of human civilization. I believe that this nation should commit itself to achieving the goal, before this decade is out, of landing a man on the moon and returning him safely to the Earth. Let that sink in for a moment. At that point, the United States had put exactly one person in space, Alan Shepard, for a grand total of 15 minutes. They had not orbited the Earth yet. They had no lunar spacecraft. They barely had a space program. And Kennedy was promising to land on the moon within 9 years. It was the equivalent of someone in the year 1900 saying, "We're going to build spaceship and fly to another planet by 1910. It was audacious almost beyond comprehension, but here is what made it work. It was not about science. It was not about exploration for its own sake. It was about power. It was about fear. It was about proving to the entire watching world that democracy and freedom could out-achieve communism. The moon was not a destination, it was a trophy. And that distinction, that the moon race was fundamentally a political competition, not a scientific one, is the single most important piece of context you need to understand everything that happened next. Because what happens to a race when one side crosses the finish line? It ends. NASA's budget in the mid-1960s was extraordinary. At its absolute peak in 1966, the space agency consumed roughly 4% of the entire United States federal budget. 4%. Today, NASA gets less than half of 1%. Think about that difference. Think about what it says about the weight that space exploration once carried in the national conversation. In those years, 400,000 Americans went to work every single day, building the hardware that would get men to the moon. Engineers, machinists, mathematicians, seamstresses sewing spacesuits by hand. Women like Katherine Johnson doing orbital calculations by hand in a room called the Colored Computing section. A story that the film Hidden Figures brought to life decades later. The Saturn V rocket, the machine that actually carried the Apollo astronauts to the moon, remains to this day the most powerful rocket ever successfully launched in the history of humanity. It stood 363 feet tall. It weighed 6.2 million pounds when fully fueled. Its 5 first-stage engines burned through 20,000 pounds of fuel every single second at liftoff. Every single second. When it launched, you could hear it 100 miles away. The ground shook like an earthquake for miles in every direction. People reported feeling the sound wave hit their chest before they could even process what they were seeing. Witnesses who were there say it is the most viscerally powerful thing they have ever experienced in their lives. And NASA built 13 of them. But here is the thing about all of that extraordinary power and ambition and money. It was entirely propped up by a political emergency that was beginning to fade. By 1968, Apollo 11's launch was just a year away, and the Cold War, while still intensely dangerous, was no longer the screaming daily panic it had been. The space race anxiety was loosening its grip. The American public's attention was being pulled in a dozen different directions: civil rights, Vietnam, political assassinations, social upheaval. The urgency that had made the moon a national obsession was slowly bleeding away. And then, on the 20th of July, 1969, Neil Armstrong stepped onto the surface of the moon, and the race was over. America had won. Now, here is where this story takes a turn that most people never learn about in school. The moment Armstrong's boot touched the lunar surface, something shifted in Washington. Almost overnight, the burning question changed from "How do we get to the moon?" to "Why are we still going to the moon?" 6 more Apollo missions had been planned. 3 of them were quietly cancelled before they even flew. Not because anything went wrong, not because it was too dangerous, but because the political reason for going had been accomplished. The trophy had been won. The Soviet Union had lost. The mission was complete. What you are about to discover in this video is that the story of why we never went back is not really about rockets or radiation or money, although all of those played a role. It is a story about what happens when human beings accomplish something for the wrong reason, when a journey is driven by fear instead of curiosity, by competition instead of wonder. It is a story about us, about human nature, about the gap between what we are capable of doing and what we actually choose to do. And by the end, you will understand not just why we stopped going to the moon, but why we are, right now, in this decade, finally, genuinely trying to go back. And this time, the reasons are completely different. But before we get there, we need to talk about what actually happened to NASA after that triumphant July day in 1969. Because the story of what followed is one of the most dramatic collapses of ambition in modern history. And it starts with a number, $20 billion. That was the final cost of the Apollo program, $20 billion, which in today's money translates to somewhere around $250 to $260 billion. For context, that is roughly equivalent to the entire annual budget of many large countries. The program had employed 400,000 people. It had consumed resources on a wartime scale. And it had worked. Beyond anyone's wildest dreams, it had worked. But the moment it worked, the people holding the checkbook started asking the question that would echo through NASA's history for the next 5 decades. Now what? That question, now what, is where everything starts to unravel. And the answer that came out of Washington in the early 1970s is one of the most consequential decisions in the history of human space exploration. But we are going to get to that in the next part of this story, because what happened inside NASA's walls after Apollo 11 is something that very few people know about, and it will completely reshape the way you understand everything that followed. We will talk about the cancelled missions, the budget cuts that gutted the agency, the politicians who genuinely believed the moon had served its purpose and there was no reason to go back, and the one quiet, devastating policy decision that essentially erased over a decade of hard-won momentum in a single stroke. You see, losing the technology to return to the moon is only half of the story. The other half is about losing the will. And understanding that distinction is the key to understanding everything. Stay with me, because the next chapter of this story is where it really gets interesting. To understand what happened after Apollo 11, you need to go back to a very specific moment in time, the summer of 1970, just 1 year after Neil Armstrong's historic footstep. NASA was already fighting for its survival. The agency had been riding an extraordinary wave of public support and government funding for nearly a decade. But that wave had crested the moment Armstrong said those famous words. The race was over, America had won, and Washington's attention had immediately turned elsewhere. The Vietnam War was consuming the country, emotionally, financially, and politically. Domestic tensions over civil rights, poverty and political corruption were reaching a boiling point, and President Nixon, who had inherited both the war and the space program, faced a simple, brutal calculation. Every dollar spent on going to the moon was a dollar not spent on things that voters cared about right now, today, on the ground. So the cuts began. They were not dramatic. They did not come with headlines or speeches. They came quietly, in budget proposals and committee decisions and line items buried in 1,000-page government documents. But their effect was devastating. NASA's budget, which had peaked at roughly $5.9 billion in 1966, was slashed year after year. By 1973, it had fallen to just under $3.3 billion. That is a cut of nearly half in just 7 years, and the agency that had once consumed 4% of the federal budget was now operating on a fraction of that. The human cost was immediate. Those 400,000 workers who had built the Saturn V, they were laid off. Engineers, machinists, technicians, people who had dedicated years of their lives to the most complex engineering project in human history were handed pink slips and sent home. Entire teams dissolved. Institutional knowledge that had taken a decade to build walked out the door with them, and once those people were gone, they were gone. Now, here is something that sounds almost unbelievable when you first hear it, but it is completely, verifiably true. NASA lost the original telemetry data from the Apollo missions, not all of it, but a significant portion of the raw data from Apollo 11. The most important spaceflight in human history was recorded on magnetic tapes that were later reused or simply lost track of in the chaos of an agency being scaled down while simultaneously trying to manage ongoing missions. For decades, researchers trying to study the original high-quality footage of the moonwalk could only access lower-resolution copies. The best recordings of one of humanity's greatest moments were gone. And then there are the blueprints, the original design documents for the Saturn V rocket, the machine that actually got us to the moon, are a subject of ongoing historical confusion. Over the years, multiple news stories have claimed that NASA lost the plans for the Saturn V. The reality is more nuanced than that, but no less troubling. The original engineering documents exist in various archives, but the institutional knowledge required to actually interpret and use them, The accumulated expertise of hundreds of thousands of engineers who spent years working on specific subsystems. That knowledge did not get stored in any archive. It lived in the minds of the people who built it, and those people retired, or moved on, or passed away. When NASA engineers decades later tried to reverse engineer certain components of the Saturn V for new rocket programs, they discovered something humbling. The documentation alone was not enough. You could have every blueprint in existence and still not be able to recreate the rocket without the human expertise behind it. Some manufacturing techniques had been lost entirely. Some materials were no longer produced. Some suppliers no longer existed. It is a phenomenon that engineers and historians call tacit knowledge, the understanding that lives in hands and habits and experience, not in written instructions, and the Apollo program lost an enormous amount of it. So when people say that NASA lost the technology to go to the moon, they are not talking about some scandal where blueprints were literally thrown in a trash can. They are describing something far more sobering, the slow, silent erosion of human expertise that happens when you stop doing something for long enough, when you let a team dissolve, when you let a generation of specialists retire without passing on what they know, when you stop flying missions because the political will to fund them has evaporated. You do not lose the knowledge overnight. You lose it piece by piece, over years and decades, until one day you look around and realize it is simply gone. But the budget cuts and the lost expertise were only part of the story. Because NASA, even in its reduced state, still had plans, ambitious ones. Before Apollo 11 even launched, NASA engineers and administrators were already dreaming far beyond the moon. They had proposals for permanent lunar bases, for crewed missions to Mars in the 1980s, for massive space stations in Earth orbit that would serve as jumping-off points for the rest of the solar system. Wernher von Braun, the legendary rocket engineer who had designed the Saturn V, had laid out a roadmap for human expansion into the solar system that would have been breathtaking if it had been followed. In 1969, the future seemed wide open. The moon was not a destination. It was the first step, and then came the decision that effectively ended that vision for a generation. In 1972, the same year Gene Cernan made his final footsteps on the moon, President Nixon approved the development of the Space Shuttle. On the surface, this sounded like progress, a reusable spacecraft, one that could fly to orbit and come back and fly again. It seemed like the next logical chapter. But the decision to build the shuttle came with a hidden cost that would define American spaceflight for the next 4 decades. The shuttle was designed not just by engineers, but by budget committees. Its final design was shaped heavily by the Air Force and by political compromises that made it far more expensive and complicated than its original concept. And critically, the space shuttle could not go to the moon. It was designed purely for low Earth orbit. The moment the shuttle was approved, the deep space human spaceflight program effectively ended. Every dollar and every engineering resource that might have gone toward maintaining and advancing lunar capability was redirected toward building and operating the shuttle. The infrastructure for going beyond Earth orbit was quietly allowed to age and decay. The last Saturn V rocket ever built, Saturn V 513, never flew. It sits today horizontal in a park outside the Johnson Space Center in Houston, Texas. You can walk alongside it, you can look up at its 5 massive engines, and you can think about the fact that this machine, capable of carrying humans to the moon, was never used. It became a lawn ornament. At this point, it is worth stopping and asking a question that I think is genuinely important. Why does this matter? Why should you care about decisions that were made 50 years ago? Here is why. The story of what happened to NASA after Apollo is not just a story about space exploration. It is a story about what happens when human societies accomplish something extraordinary for the wrong reasons and then fail to find new reasons to keep going. It is a story about short-term thinking versus long-term vision, about the gap between what we are capable of as a species and what our political systems are actually designed to support. And it is a story that is playing out again right now in real time, because we are, as of this very decade, trying to go back to the moon. NASA's Artemis program has been working toward landing the first woman and the next man on the lunar surface. Commercial companies like SpaceX are developing rockets more powerful than anything that existed since the Saturn V. There is a genuine growing movement to return to the moon, and this time, not as a political stunt, but as the foundation for something much larger. But to understand whether this new effort will succeed or whether it will repeat the mistakes of the past, you need to understand something deeper about the challenge of returning to the moon. Because the gap between we did it once and we can do it again is much wider than most people realize. If you are finding this journey through space history as fascinating as I am, now is a great time to hit that subscribe button and leave a like on this video. It genuinely helps this channel grow, and it means I can keep making deep dives like this one. You're exactly the kind of curious, thoughtful person this channel exists for. Now, let's talk about radiation, because one of the most uncomfortable truths about returning to the moon, one that does not get discussed nearly enough in popular coverage of space exploration, is that the journey there is genuinely, measurably dangerous in ways that we are only beginning to fully understand. Space is not empty. It looks empty, but it is filled with radiation, high-energy particles streaming out from the sun, and even more energetic cosmic rays arriving from deep space, from supernovae and neutron stars, and processes happening in galaxies billions of light-years away. On Earth, you are protected from almost all of this by two things: the planet's magnetic field, which deflects charged particles, and the atmosphere, which absorbs the ones that get through. The moment you leave Earth orbit, both of those shields disappear. The Apollo astronauts were exposed to radiation levels that would never be permitted in any modern occupational safety framework. Most of them flew their missions during relatively calm periods of solar activity, which limited their exposure somewhat. But the risk was real, and it was known. NASA accepted it because the political imperative to beat the Soviets outweighed almost every other consideration. A study published in 2016 in the journal Scientific Reports looked at the mortality rates of Apollo astronauts compared to other astronaut groups and non-astronaut test pilots. The researchers found that Apollo astronauts had significantly higher rates of cardiovascular disease-related death than their counterparts who had never left low Earth orbit. The sample size was small. There were not that many Apollo astronauts, but the finding raised serious questions about the long-term health effects of deep space radiation exposure. And the moon itself offers almost no protection. It has no global magnetic field, no atmosphere. The surface is bathed in radiation every single day. A lunar base would need to be heavily shielded, probably built underground or covered in thick layers of lunar regolith, the fine grey dust that covers the surface, to be livable for extended periods. This is not an insurmountable problem, but it is a genuinely hard one, and it illustrates something important about the difference between the Apollo era and today. In 1969, the goal was to get there and come back, full stop. The question of whether you could actually live there, work there, build something there, that was somebody else's problem, for some future generation to figure out. That future generation is us. And that brings up something even more fascinating and more unsettling about the moon that most people have never considered. The Apollo astronauts brought back 382 kilograms of lunar rock and soil. That is roughly 842 pounds of another world, sitting in laboratories and storage facilities, having been studied by scientists for over 50 years. And what they found in those rocks tells a story about the moon and about Earth that is genuinely mind-bending. The leading scientific theory for the origin of the moon is called the giant impact hypothesis, and it goes like this. About 4.5 billion years ago, very early in the solar system's history, the young Earth, which was still forming, still cooling from the chaos of planetary formation, was struck by another planet. Not an asteroid, a planet. Scientists have named it Theia. Theia was roughly the size of Mars. It hit the early Earth at an angle at tremendous speed. The collision was so violent that it partially vaporized both bodies. An enormous cloud of debris was blasted into orbit around the Earth. Molten rock, vaporized material, fragments of both worlds mixed together, and over hundreds of thousands of years, that debris slowly clumped together under gravity and formed the moon. This means the moon is, in a very literal sense, made partly of Earth. It is a piece of our own planet, flung into space by a cosmic collision 4.5 billion years ago. When Gene Cernan picked up a rock on the lunar surface, he was, in a sense, holding a fragment of the ancient Earth. The chemical evidence from the Apollo samples strongly supports this theory. The ratio of oxygen isotopes in lunar rocks is remarkably similar to Earth rocks, far more similar than you would expect if the moon had formed independently. This points strongly toward a common origin. And here is the part that connects to something bigger. The moon's formation may have been crucial to the development of life on Earth. The moon stabilizes Earth's axial tilt. Without it, our planet might wobble dramatically on its axis over millions of years, causing catastrophic climate shifts that could prevent the kind of stable, long-term conditions that allowed complex life to evolve. The moon raises our tides, which may have played a role in the emergence of early life in coastal environments. The moon is not just a pretty object in our sky, it is in a very real sense, a partner in the story of life on Earth. And we stopped visiting it. There is something almost poetic about that. We share a common origin with the moon. It helped make us possible. And the last time a human being stood on its surface, the reason we had gone there in the first place was to score points in a geopolitical competition that no longer exists. The moon deserves better than that. And here is what I want you to hold on to as we move into the next part of this story. The decision to stop going to the moon was not inevitable. It was not a law of nature. It was a choice, a series of choices made by specific people in specific political and economic circumstances. Choices that could have been made differently. In the next part, we are going to go deeper into the technical reality of what returning to the moon actually requires, and why, despite all the progress of the last 50 years, it has proven so much harder than most people expected. We will talk about the engineers and scientists who spent their careers trying to keep the dream alive, and the very specific moments where the window for returning seemed to open and then quietly closed again. Because the story of the moon is not over, not even close, and the next part is the one we are living through right now. Let me ask you something. If someone told you that the most powerful rocket ever built in the 21st century, a machine taller than the Statue of Liberty, generating more thrust than any vehicle in human history, had already launched, and most people had no idea it existed, would you believe them? Because that is almost exactly what happened. In November of 2022. NASA launched the Space Launch System, the SLSC, for the very first time. It carried an uncrewed capsule called Orion on a mission called Artemis 1. The rocket stood 322 feet tall. Its core stage engines and solid rocket boosters generated 8.8 million pounds of thrust at liftoff, actually surpassing the Saturn V's first stage thrust for a brief moment during ascent in certain configurations. Depending on how you measure it, it flew around the moon, it came home, it worked. And yet, if you asked most people on the street whether NASA had recently launched the most powerful rocket in decades toward the moon, the majority would look at you blankly. That disconnect between what is actually happening in space exploration right now and what the general public knows about it is one of the most fascinating and frustrating aspects of this whole story. Because we are living through a genuine revolution in space exploration, and most of us are completely missing it. To understand where we are today, you first need to understand what went wrong in the decades between Apollo and now, because it was not just one thing. It was a perfect storm of budget pressure, political indifference, failed programs, and a fundamental misunderstanding of what space exploration actually requires to sustain itself over the long term. After the Space Shuttle was approved in 1972, NASA spent the next 3 decades primarily focused on low Earth orbit. The shuttle flew 135 missions between 1981 and 2011. It deployed the Hubble Space Telescope. It helped build the International Space Station. It carried out extraordinary science, but it never left Earth orbit, not once, and it was expensive. Staggeringly, almost incomprehensibly expensive. The original promise of the shuttle program was that reusability would make spaceflight cheap, that each mission would cost something like $10 million, making routine access to space a reality. What actually happened was almost the opposite. Each shuttle mission ended up costing somewhere between $500 million and $1.5 billion, depending on how you account for the overhead. The shuttle was operationally complex in ways that its designers had underestimated. It required an army of technicians to refurbish it between flights. Its heat shield tiles, the ceramic plates that protected it during re-entry, had to be individually inspected and often replaced before every mission. The gap between the dream and the reality of the space shuttle is in many ways a microcosm of the entire post-Apollo period. The ambition was enormous. The execution was constrained at every turn by budget limitations, political compromises, and the sheer difficulty of operating in space. And then, twice, it killed people. The Challenger disaster on the 28th of January 1986 killed all 7 crew members 73 seconds after launch when an O-ring seal on one of the solid rocket boosters failed in cold temperatures. The Columbia disaster on the 1st of February 2003 killed all 7 crew members during re-entry when a piece of foam insulation that had struck the orbiter's wing during launch had created a hole that allowed superheated plasma to penetrate the structure. Both disasters were, in hindsight, failures not just of engineering but of organizational culture, cases where warning signs had been seen, raised, and ultimately not acted on with the urgency they deserved. The Rogers Commission report on Challenger and the Columbia Accident Investigation Board report on Columbia both pointed to systemic problems within NASA that went far beyond a faulty O-ring or a piece of foam. Each disaster grounded the shuttle fleet for years. Each one consumed enormous institutional energy in investigation, redesign, and rebuilding of public trust, and each one reinforced, in the minds of politicians and budget writers, the question that had been hovering over human spaceflight since the end of Apollo: is this worth it? Meanwhile, in the background, a succession of deep space human spaceflight programs were proposed, funded, partially developed, and then cancelled, a cycle so repetitive it almost feels like a dark comedy. In 1989, President George H.W. Bush announced the Space Exploration Initiative, a plan to return to the Moon and then go on to Mars. NASA estimated it would cost $500 billion over 30 years. Congress looked at that number and immediately lost interest. The program quietly died. In 2004, President George W. Bush announced the vision for space exploration, a plan to retire the space shuttle, build a new rocket called Ares, develop a new capsule called Orion, return to the moon by 2020, and then go to Mars. This one actually got funded. Billions of dollars were spent, teams were hired, hardware was designed and tested, and then in 2010, President Obama cancelled it. Not because it was not working, because a review panel called the Augustine Commission found that the program, as funded, would not actually reach the moon by 2020, or possibly ever, without a significant budget increase that the administration was not willing to provide. The program was cancelled, and most of the Ares rocket work was scrapped. The engineers who had spent years on that program were devastated. Again, there is a phrase that gets used in the aerospace industry to describe this pattern: killing it before it flies. The cycle of proposing ambitious space programs, partially funding them, and then cancelling them before they reach fruition has been one of NASA's most persistent and painful patterns since Apollo. Each cancellation does not just waste the money already spent, it destroys the team, the momentum, and the institutional knowledge that had been building. So, by the time the Artemis program was formally announced in 2017, and given a concrete mandate to land humans on the moon by 2024, a deadline that has since been pushed back, the aerospace community had a very understandable reaction. We have heard this before, and that skepticism is not cynicism. It is the accumulated memory of decades of disappointment, of programs that started with fanfare and ended in cancellation notices, of rockets that were designed, partially built, and then turned into museum pieces. But here is where the story takes a genuinely new turn, because something happened in the 2010s that has fundamentally changed the landscape of space exploration in a way that has no real precedent in the entire history of the field. Private companies entered the game. For real, for most of the history of spaceflight, rockets were built by governments or by large aerospace contractors working almost exclusively for governments. Companies like Boeing and Lockheed Martin built rockets the way defense contractors build aircraft carriers, on cost-plus contracts where the government pays whatever it costs plus a guaranteed profit margin. This system is not designed to produce innovation or efficiency. It is designed to produce reliability and political support, keeping jobs in the right congressional districts, spreading contracts across the right states. The result was rockets that worked, but were extraordinarily expensive and improved only slowly. Then Elon Musk founded SpaceX in 2002, and everything changed. Musk's core insight was almost offensively simple. The reason rockets are expensive is not because space is hard. It is because no one had tried seriously to apply modern engineering and manufacturing techniques to the problem with a genuine profit motive pushing for efficiency rather than a cost-plus contract that rewarded spending more. SpaceX set out to build rockets that were not just cheaper, but reusable in a way that the space shuttle had failed to achieve. And after years of failures, near bankruptcies, and moments where the entire company was on the edge of collapse, they pulled it off. In December of 2015, a SpaceX Falcon 9 rocket launched a payload to orbit, separated its first stage, and then that first stage flew itself back to Earth and landed vertically on 4 legs at the launch site. It was one of the most visually stunning moments in the history of rocketry. A rocket had returned from space and landed itself, ready to fly again, and then they did it again, and again, and again. Booster cores from the Falcon 9 family have now been reused over 20 times each. The cost of launching a kilogram to orbit has dropped dramatically compared to what it was in the shuttle era. But that was just the beginning. Because SpaceX's ambitions were always pointing somewhere much further than low Earth orbit, the Starship rocket system currently being developed and tested by SpaceX at their facility in Boca Chica, Texas, is, if it achieves its design goals, unlike anything that has ever flown. It is designed to be fully and rapidly reusable. Both stages, the Super Heavy booster and the Starship upper stage, are designed to return to Earth and be caught by mechanical arms on the launch tower, refueled and flown again within hours. Its payload capacity, if fully operational, would dwarf anything in the current fleet. Its intended cost per launch, if reusability works as designed, could be lower by an order of magnitude compared to existing heavy-lift rockets. NASA has already selected a version of Starship as the human landing system for the Artemis program, the vehicle that will actually carry astronauts from lunar orbit down to the surface of the Moon. This is a remarkable development. NASA, the agency that built the Saturn V, is depending on a private company's rocket to actually land its astronauts on the lunar surface. That tells you everything about how dramatically the space industry has changed, and SpaceX is not alone. Blue Origin, founded by Jeff Bezos, has been developing its own large rocket, the New Glenn, and its own lunar lander. Rocket Lab, a smaller company, has been launching small satellites at a pace and cost that would have been unimaginable a decade ago. A whole ecosystem of commercial space companies has emerged, building everything from space stations to lunar rovers to satellite constellations. The commercialization of space is not a future trend. It is happening right now. And it is one of the primary reasons that the return to the Moon, despite all the false starts and cancelled programs of the past 50 years, feels more genuinely achievable today than at any point since Apollo 17 lifted off in December of 1972. But there is another dimension to this story that does not get nearly enough attention, and it is the dimension that, in my view, makes the return to the Moon feel less like a repetition of the past and more like the beginning of something genuinely new. It is the science, because in the 50 years since the last Apollo mission, our understanding of the Moon has been transformed. And what we have learned has made it not less interesting, but dramatically more so. In 2008 and 2009, a series of spacecraft, including India's Chandrayaan-1 orbiter and NASA's Lunar Reconnaissance Orbiter, made a discovery that completely changed the strategic and scientific calculus for returning to the Moon. Water ice, not liquid water, not flowing rivers, but frozen water, billions of tons of it, locked in the permanently shadowed craters near the Moon's poles, regions so deep and so tilted away from the Sun that they have not seen sunlight in billions of years. Temperatures in these craters drop to around -240 degrees Celsius, making them among the coldest places in the entire solar system. And in those frozen shadows, water ice has been accumulating for billions of years, deposited by comets and asteroids and possibly by the solar wind itself. This changes everything. Water on the Moon is not just scientifically fascinating, though it absolutely is. It is potentially rocket fuel. Water molecules can be split into hydrogen and oxygen using solar power, a process called electrolysis. Liquid hydrogen and liquid oxygen are exactly what rocket engines burn, which means the Moon's polar ice deposits could, in principle, serve as a refueling station for spacecraft heading deeper into the solar system. Mars, the asteroids, the outer planets, all of them become significantly more accessible if you can launch from the Moon rather than from the bottom of Earth's deep gravity well. This is why space agencies and private companies are not just interested in going back to the Moon. They are interested in learning how to stay there, how to extract resources, how to build infrastructure, how to turn the Moon from a destination into a departure point. The Moon, it turns out, may not be the finish line of human space exploration. It may be the gas station. And this is where the story gets truly cosmic in its implications. Because when you zoom out far enough, when you look at the moon not as a Cold War trophy or a science destination, but as a stepping stone, you start to see the entire arc of human space exploration in a completely different light. We are a species that emerged on one small planet, orbiting one ordinary star, in the outer spiral arm of one galaxy among 2 trillion others. For the vast majority of our existence, we had no idea that the lights in the night sky were other suns, no idea that some of them had planets, no idea that the universe was billions of years old and billions of light years across. We figured all of that out in roughly the last 400 years, a cosmic eye blink, and now, for the first time in the 4 billion-year history of life on this planet, one species has developed the ability to leave its home world, to go somewhere else, to pick up a rock from another body in space and bring it home and study it. That is extraordinary. That is unprecedented. And the moon that has watched over every human civilization that has ever existed, that has pulled our tides and lit our nights and driven our calendars, the moon is the first step beyond the cradle. Whether we take that step, and whether we take it wisely, for the right reasons, with the right intentions, is one of the defining questions of our time. But here is the thing I have not told you yet. The thing that puts all of this in a perspective that I think will genuinely change how you see the night sky. The reason we are going back to the moon, the deep reason, underneath all the politics and the budgets and the commercial interests, is the same reason we went in the first place. The same reason human beings have always pushed beyond the horizon, into the unknown. We are curious. It is in our nature. It is written into us at a level as fundamental as anything else that makes us human. And there is something waiting on the moon, something that scientists have been discussing for years, something that connects the story of the moon to the deepest questions about life, the universe, and our place in it. That makes returning there not just exciting but arguably essential. We are going to get to that, I promise you. But first, we need to talk about something that sounds almost mundane compared to the cosmic scale of this story, but is, in practice, one of the biggest obstacles standing between us and the moon right now. It is the problem of dust, lunar dust, 2 words. But behind them lies one of the most fascinating, most dangerous, and most underestimated challenges in the entire field of space exploration. And you are absolutely not going to believe what it does. Imagine you are standing on the moon. You have just finished a 6-hour spacewalk across the lunar surface. You climb back into the lander, seal the hatch, and repressurize the cabin. You pull off your helmet, and immediately you notice something. The air smells like gunpowder, not faintly, not as a subtle background note. The smell hits you clearly, distinctly, sharp and acrid, like you are standing next to a firing range. You look down at your suit and you see that it is covered in a fine grey-black powder that clings to everything it touches. You try to brush it off. It does not brush off. It has worked its way into the fabric, into the seams, into every tiny gap and crevice in the material. That is lunar dust. And almost every Apollo astronaut who walked on the surface described the same experience. Harrison Schmitt, the geologist who flew on Apollo 17 and remains the last scientist to walk on the moon, developed what he described as lunar dust hay fever after his first moonwalk. His eyes watered. His throat was scratchy. His symptoms persisted for hours after returning to the cabin. He was breathing in the moon. This was not an isolated incident. Multiple Apollo astronauts reported respiratory irritation after exposure to lunar dust that had been tracked into their spacecraft. And at the time, NASA had larger things to worry about, getting people to the moon and back alive, so the dust problem was noted, documented, and largely set aside for future missions to deal with. But future missions never came, and so the dust problem was never truly solved. Here is why lunar dust is unlike anything you have ever encountered on Earth. On our planet, Dust and sand particles are constantly being worn down. Wind and water and friction round off their sharp edges over millions of years. Pick up a handful of beach sand and look at the grains under a microscope and you will see rounded, smooth particles shaped by billions of collisions over enormous spans of time. The Moon has none of that. The Moon has no atmosphere, no wind, and no liquid water. Its surface has been bombarded by micrometeorites, tiny particles of rock and metal traveling at extraordinary speeds for 4.5 billion years. Each impact vaporizes a tiny amount of the surface material, which then condenses into ultrafine particles. Those particles are not rounded, they are jagged, they are sharp at a microscopic level, with edges and points that have never been softened by any erosive process. They are also electrostatically charged. During the lunar day, solar radiation strips electrons from the surface material, giving it a positive charge. This means lunar dust does not just sit on surfaces, it actively clings to them. It is drawn to anything it touches by electrostatic attraction. It coats visors and reduces visibility. It works its way into mechanical joints and grinds them down. It clogs filters. It degrades solar panels by coating their surfaces and reducing the amount of sunlight they can absorb. During the Apollo missions, the dust degraded equipment measurably over just a few days of surface operations. Astronaut suits, which were designed to be worn multiple times, showed significant wear after just 2 or 3 moonwalks because the razor-sharp dust particles were slowly cutting into the fabric at a microscopic level. Some of the hinges and joints on equipment became increasingly stiff as dust accumulated inside them. Now think about what that means for a permanent lunar base, a structure that needs to function not for a few days, but for months or years. Every solar panel, every airlock seal, every mechanical joint, every piece of equipment that human inhabitants depend on for their survival, all of it constantly being coated, infiltrated, and degraded by a dust that clings like a magnet and cuts like ground glass. Engineers who work on lunar surface systems do not talk about lunar dust as a nuisance. They talk about it as one of the primary engineering challenges of long-term lunar habitation. Some researchers have described it, without exaggeration, as potentially the single most dangerous material on the Moon. And that is before you get to the health implications. The jagged, angular shape of lunar dust particles makes them particularly dangerous if inhaled. On Earth, the particles most dangerous to human lungs, silica dust from mining, asbestos fibers, are dangerous largely because of their sharp, fibrous shapes, which can lodge in lung tissue and cause progressive, irreversible damage. Lunar dust has a similar physical profile, but at an even finer scale. Particles small enough to penetrate deep into the lungs, what scientists call respirable particles, are present in significant quantities in lunar regolith. The long-term health effects of lunar dust inhalation are not fully understood because no human has ever been exposed to it for longer than a few days. The Apollo astronauts' exposure was brief by any standard of occupational health, but the extrapolations from what we know about similar particles on Earth are sobering. NASA researchers studying the toxicology of lunar dust have found that in laboratory tests, simulated lunar dust causes significant damage to human lung cells and brain cells, more damage in some studies than quartz dust, which is itself a known carcinogen. These are early results from simulated materials rather than real lunar regolith, and the science is still developing. But the direction of the findings is not reassuring. For anyone living on the Moon, in a base conducting regular surface operations, constantly cycling in and out of airlocks, managing dust exposure is not optional, it is a matter of survival. Engineers are currently working on everything from electrostatic dust shields that would repel particles using electric fields to specialized filtration systems to airlock designs that minimize the amount of dust tracked inside. None of these solutions are fully mature. All of them are works in progress. But here is the thing about challenges like this one. They are real, they are serious, and they are also exactly the kind of problems that human ingenuity is extraordinarily good at solving when it is properly motivated. And right now, the motivation is intensifying, because the race to the moon is no longer just a story about NASA and the United States. It has become once again a story about geopolitics, about competition between great powers, about who controls the resources and the strategic high ground of cislunar space, the region between Earth and the Moon, and the country that has changed the equation more than any other is China. In December of 2013, China landed a robotic spacecraft on the Moon. The Chang'e 3 mission deployed a rover called U2, Jade Rabbit, onto the lunar surface. It was the first soft landing on the Moon in 37 years, since the Soviet Lunar 24 mission in 1976. The world noticed, in January of 2019, China did something that no country had ever done before in the entire history of space exploration. The Chang'e 4 mission landed on the far side of the Moon, the hemisphere that permanently faces away from Earth, which had never been visited by any spacecraft that touched down. Because the far side of the Moon is always facing away from Earth, direct radio communication is impossible. China solved this by placing a relay satellite in a special orbit above the Moon's far side, allowing signals to bounce between the lander and mission control back on Earth. It was a genuine first, a real achievement. And it came from a country whose space program, just 20 years earlier, had been considered a distant third behind the United States and Russia. China's lunar program has been moving forward with a consistency and a long-term focus that stands in sharp contrast to NASA's start-and-stop history of the past 50 years. The Chang'e 5 mission, in late 2020, returned lunar samples to Earth for the first time since the Soviet lunar program in the 1970s. China is now developing the infrastructure for a permanent robotic presence on the Moon, with plans for a crewed lunar mission in the 2030s. And China has been explicit about its interest in the lunar South Pole, the same region where NASA's Artemis program intends to land. The reason both programs are targeting the same area of the Moon is exactly what we discussed earlier: water ice. The permanently shadowed craters near the South Pole are the most accessible deposits of lunar water ice identified so far. Whoever establishes a permanent presence there first will have a significant strategic and scientific advantage. This is where the conversation in Washington starts to sound uncomfortably familiar. In congressional hearings and policy discussions over the last several years, China's lunar program has been cited repeatedly as a reason to accelerate NASA's Artemis timeline. The language used by some officials has been strikingly similar to the Cold War framing that drove the original Apollo program. The idea that the Moon represents a strategic asset, that falling behind China in space would be a significant geopolitical setback, that competition is the necessary motivation for the investment required. Bill Nelson, the NASA administrator, said publicly in 2023 that there is, in his view, a space race between the United States and China, and that the stakes are high. There is an obvious irony here. The original lunar program was driven by competition with the Soviets, and it collapsed the moment that competition ended. Now, 50 years later, a new competition is emerging, with a different rival, but with structurally similar dynamics. Will the competition with China sustain the Artemis program through the inevitable budget pressures and political changes that every long-duration space program faces? Or will history repeat itself, with the initial urgency fading once the political moment passes, leaving another half-built program in its wake? Nobody knows the answer to that question yet. but the people who study the history of space policy are watching very carefully, because the pattern has repeated enough times that you would have to be willfully optimistic not to see it. And yet, and this is important, the situation today is genuinely different from the 1960s in at least one crucial way. In the Apollo era, the only entity capable of sending humans to the moon was a government, period. Specifically, the American government, with the full weight of the federal budget behind it. When political will collapsed, the program collapsed with it. There was no backup. Today there is SpaceX, there is Blue Origin. There is a growing commercial space ecosystem with financial incentives that are independent of any single government's political priorities. Elon Musk has stated repeatedly that his personal goal is to make humanity a multi-planetary species, to establish a self-sustaining city on Mars. The moon, in his framework, is infrastructure on the way to that goal. His motivation is not going to evaporate because of a change in administration in Washington. Whether you find that reassuring or alarming, and reasonable people have argued both ways, it represents a structural change in the economics of space exploration that did not exist during Apollo. For the first time, the push to go back to the moon and beyond is being driven not just by government agencies subject to political cycles, but by private entities with their own agendas and their own financial resources. This does not guarantee success. Private space companies have failed before and will fail again. The challenges are real, the timelines are uncertain, and the technology is still being developed. But the presence of commercial players in the game fundamentally changes the resilience of the overall effort in a way that is genuinely new. Now, I want to step back from the politics and the engineering for a moment, because there is a scientific story unfolding right now on the moon, or rather, around it and beneath its surface, that I think is the most underreported aspect of this entire narrative. It is the story of what the moon can tell us about the early solar system, about the formation of planets, about the conditions that existed in the first billion years of Earth's history, a period we call the Hadean Eon, named, appropriately enough, after the ancient Greek underworld. Here is the problem. The Earth's geological record from its first billion years is almost entirely gone. Our planet is geologically active. Its crust is constantly being recycled through plate tectonics, volcanic activity and erosion. The oldest rocks found on Earth are just over 4 billion years old, and they are extraordinarily rare. The conditions that existed during the planet's first half-billion years, when it was still cooling from formation, when life may or may not have been beginning, when the heavy bombardment of asteroids was reshaping the inner solar system, are largely invisible to us. But the moon is different. The moon is geologically dead. It has been geologically inactive for billions of years. Its surface is a record, scarred by impacts, yes, but not erased by volcanism or tectonics. The rocks near the lunar poles, preserved in those cold, shadowed craters, may be among the oldest intact planetary materials accessible to human explorers anywhere in the solar system. Studying them could tell us things about the early Earth and about the conditions under which life first appeared that we simply cannot learn any other way. The moon is, in a very real sense, a fossil, a 4.5 billion-year-old record of the solar system's violent youth, sitting 240,000 miles away, waiting to be read. And here is a fact that connects that ancient history to something deeply personal. Every atom of calcium in your bones, every atom of iron in your blood, every atom of oxygen you are breathing right now, those atoms were forged inside stars that lived and died before our solar system even formed. When those stars reached the end of their lives, some in slow, expanding exhalations called planetary nebulae, others in the cataclysmic explosions we call supernovae, they scattered those atoms across space, and some of those atoms over millions of years drifted into the cloud of gas and dust that eventually collapsed under gravity to form our sun, our planets, and eventually us. The rocks on the moon contain those same atoms. When an Apollo astronaut held a lunar sample in a gloved hand, they were holding material that had traveled billions of years and billions of miles to be there. Material that connects, in an unbroken chain of cause and effect, to the deaths of ancient stars and the birth of our solar system. You are made of the same stuff as the moon, the same stuff as the stars. The boundary between us and the universe is far less clear than it appears from the inside of your own skull. That is not poetry, that is nuclear physics. And it is one of the reasons that understanding the moon, really understanding it, not just visiting it for a few days and coming home, matters in ways that go far beyond any political competition or commercial interest. But none of this, not the science, not the geopolitics, not the commercial revolution, fully answers the question that started this whole story. Why did it take 50 years? We have talked about the budget cuts, the political abandonment, the Shuttle era's focus on low Earth orbit, the cancelled programs, the lost expertise, the dust, the radiation, the sheer cost and difficulty. All of those are real, all of them contributed. But I think there is a deeper answer, one that gets at something fundamental about human nature and the way our societies make decisions, one that explains not just why we stopped going to the moon, but why we have consistently failed to sustain the kind of long-term visionary commitments that achievements like Apollo require. And to find that answer, we need to go back to a conversation that happened inside NASA in the early 1970s, a conversation that very few people know about, but that shaped the next 50 years of human spaceflight more than almost any other single decision. It was a conversation about what space exploration is actually for. There is a question that does not get asked enough in conversations about space exploration. Not can we do it, not how much will it cost, not even when will we go back. The question is this: why do we go at all? It sounds almost too simple, too philosophical, the kind of question you might expect to hear in a college seminar, not in a congressional budget hearing or an engineering review. And yet it is the question that underlies every single decision ever made about human spaceflight, whether people knew they were answering it or not, because the answer you give to that question determines everything. It determines how you fund it, how you prioritize it, how you sustain it through decades of budget pressure and political change and public indifference. And most importantly, it determines whether you keep going when the original reason for going has disappeared. In the early 1970s, NASA faced a version of this question directly, and the way they answered it, or rather, the way they failed to answer it clearly, set the agency on a path that it is in many ways still trying to find its way off of. Here is the context you need. By 1972, it was clear to everyone inside NASA that the Apollo program was ending, the moon landings were winding down, the political momentum was gone, the budget was shrinking, and the agency was facing an existential question: what do we do next? There were, broadly speaking, two camps inside NASA at the time. Two very different visions for what the space program should become. The first camp, represented most visibly by Wernher von Braun and a number of the agency's senior engineers, believed that the purpose of human spaceflight was exploration and ultimately the expansion of human civilization beyond Earth. In their view, Apollo was not an endpoint, it was proof of concept. The moon was step one. Next came a permanent lunar base, then a crewed mission to Mars, then, over generations, the gradual extension of human presence throughout the solar system. This was a long-term, civilizational vision, one that required sustained commitment over decades and centuries, not just years. The second camp was more pragmatic, more politically aware. They understood that the era of blank check funding for space exploration was over, and that NASA needed to justify its existence in terms that Congress and the public could relate to on a more immediate level: jobs, economic spin-offs, national security applications, practical technological benefits that could be pointed to and measured. In their view, the agency needed to become more like a utility, providing reliable, cost-effective services rather than chasing heroic one-time achievements. The Space Shuttle was, in many ways, the compromise between these two visions. It was presented as a practical, reusable vehicle that would make spaceflight routine and affordable, satisfying the pragmatists. But it was also imagined, by the explorers in the agency, as the first piece of infrastructure in a larger architecture that would eventually take humans back to the Moon and on to Mars. What actually happened was that the shuttle satisfied neither vision completely. It was not cheap or routine, and it never led to the deeper exploration its most ardent supporters had hoped for. But the more important consequence of this moment was subtler than any specific program decision. It was the gradual loss of a clear shared answer to the question of why human beings should go to space at all. There was a man named Carl Sagan who thought about this question more deeply than almost anyone else of his generation. You probably know his name. You may have seen images of him, the turtleneck, the warm eyes, the particular way he had of making the universe feel both vast and intimate at the same time. His television series Cosmos, which first aired in 1980, is still one of the most watched science documentary series in history. His ability to communicate the beauty and significance of science to ordinary people was, and remains, almost unparalleled. But Sagan was not just a communicator. He was a working scientist, an astronomer and planetary scientist who contributed real research to our understanding of the solar system. And he was, throughout his life, one of the most thoughtful voices on the question of why space exploration matters. Sagan's answer to that question was not primarily strategic or economic. It was evolutionary, and it was philosophical, and it was deeply connected to the way he understood what human beings are. He argued that exploration is not something we choose to do, it is something we are. The drive to go over the next hill, to see what is on the other side of the ocean, to push beyond the edge of the known world, that is not a luxury or an indulgence. It is one of the defining characteristics of our species. It is part of what made us human in the first place. And the moment we stop exploring, the moment we decide that we have gone far enough and seen enough, and that there is nothing worth risking anything for beyond the next comfortable horizon, something essential about us begins to die. He was also deeply aware of another argument for space exploration that was less romantic but arguably more urgent: the fragility of a civilization confined to a single planet. In his book Pale Blue Dot, named after the famous photograph taken by the Voyager 1 spacecraft in 1990, showing the Earth as a tiny point of light suspended in the vast darkness of space, Sagan wrote words that I think deserve to be heard in full. Look again at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam. And his conclusion from this was not despair, it was urgency. If everything we are and everything we have ever been exists on that single mote of dust, then the responsibility to spread beyond it, to become a multi-world species, to ensure that no single catastrophe could end the entire human story, That responsibility is not optional. It is perhaps the most important long-term project our civilization could undertake. Sagan died in 1996. He did not live to see SpaceX or the Artemis program or the commercial space revolution, but his framing of the question, "Why do we go?" remains the most honest and most complete answer I have ever encountered. We go because we are explorers by nature. We go because putting all of our eggs in one planetary basket is an existential risk. And we go because the universe is astonishing and we are the only known beings in it capable of appreciating that astonishment, and that fact alone carries a kind of responsibility. Now, let me tell you about a moment that most histories of the space program skip over entirely. In the spring of 1970, just months after Apollo 11's historic landing, a group of scientists and researchers gathered for a conference in Vienna, Austria. The topic was the long-term future of human civilization in space. These were not dreamers or science fiction enthusiasts. They were serious researchers, physicists, biologists, engineers, social scientists, trying to think rigorously about what a sustained human presence beyond Earth would actually require. One of the ideas that emerged from that period, developed most fully by the Princeton physicist Gerard K. O'Neill in the mid-1970s, was so radical and so complete that it deserves more attention than history has given it. O'Neill proposed that the future of human civilization in space did not lie on planetary surfaces at all, not on the Moon, not on Mars, but in large rotating space habitats, artificial worlds built in space that would use rotation to simulate gravity and could house tens of thousands of people in shirt-sleeve environments with their own ecosystems, farms and cities. His calculations showed that these habitats were not fantasy. They were, in principle, achievable with technologies that existed or were within reach. The materials could come from the Moon and from asteroids, avoiding the enormous energy cost of lifting everything out of Earth's gravity well. The habitats could be placed at gravitationally stable points in space called Lagrange points, where they would require minimal energy to maintain their positions. O'Neill's vision was breathtaking in its ambition and its specificity. He wrote about it in a book called The High Frontier, published in 1976, which became enormously influential in certain circles. NASA studied his ideas seriously. A summer study in 1975, conducted with NASA's support, produced a detailed technical report on the feasibility of space colonization along the lines O'Neill had proposed, and then the political winds shifted, the budgets tightened, and the idea faded from mainstream discussion. But it never entirely disappeared. And today, with commercial space companies building the economic foundation for a much larger human presence beyond Earth, and with figures like Jeff Bezos explicitly citing O'Neill's work as an inspiration for Blue Origin's long-term vision, the ideas of that era are experiencing a quiet renaissance. The point is not that O'Neill's specific vision will be realized exactly as he described it. The point is that the question of humanity's long-term future in space has been thought about seriously, rigorously, and optimistically by brilliant people for much longer than most people realize. The ideas are there. The technical foundations have been studied. What has been missing, again and again, is the sustained commitment to act on them. That gap between vision and commitment is, I think, the real answer to the question we started with. Why haven't we been back to the Moon for 50 years? Not primarily because of money, not primarily because of technology, not primarily because of radiation or dust, or the loss of expertise, though all of those are real obstacles. The deepest reason is this: we built the greatest exploration program in human history on a foundation of fear and competition, and when the fear faded and the competition ended, the foundation crumbled. We never replaced it with something more durable. We never built a broad, deep, sustained public consensus that space exploration matters for its own sake, for the sake of knowledge, for the sake of survival, for the sake of what it means to be a curious, exploring species in an astonishing universe. We did the most extraordinary thing our civilization had ever done, for reasons that turned out to be temporary. And when those reasons evaporated, we walked away. That is the brutal truth at the heart of this story. But here is where I want to push back, gently but firmly, against the most pessimistic reading of that history. Because I think despair about this is as unwarranted as naive optimism. Consider what has actually happened in the 50 years since Apollo 17. We built the Hubble Space Telescope, which transformed our understanding of the universe so completely that it is difficult to overstate. Before Hubble, we knew galaxies existed but could not see them in detail. After Hubble, we could see galaxies colliding, stars being born in pillars of gas and dust, the light from objects so distant that we were looking back almost to the beginning of time itself. We launched the Voyager probes, which gave us our first close-up views of Jupiter, Saturn, Uranus, and Neptune, worlds that no human had ever seen as anything other than points of light. Voyager 1 is now in interstellar space over 23 billion kilometers from the Sun, still sending back data. It is the most distant human-made object in existence. When its signal reaches us, it has been traveling for over 22 hours at the speed of light. We landed rovers on Mars. Not one or two, but multiple generations of increasingly sophisticated robots, culminating in the Perseverance rover, which landed in 2021 and has been drilling into Martian rock, analyzing its chemistry and searching for signs of ancient microbial life ever since. The Ingenuity helicopter, which traveled with Perseverance, made the first powered, controlled flight on another planet, in the thin Martian atmosphere. On another world, we built the International Space Station, an outpost in low Earth orbit continuously inhabited by human beings since November of 2000. As of this recording, there has not been a single day in over 2 decades when human beings were not living in space. That is remarkable. That is a genuine sustained human presence beyond Earth, modest in scale but real. And we launched the James Webb Space Telescope, which began sending back images in 2022 that made people cry. Images of galaxies forming when the universe was just a few 100 million years old. Images of exoplanet atmospheres revealing the chemical signatures of distant worlds. Images of a cosmos so rich and so vast and so beautiful that they make every argument about whether space exploration is worth the cost feel almost absurd. We did not stop exploring. We never stopped. We just stopped sending people to the moon. And that distinction matters because it means the knowledge, the infrastructure, the institutional capability, and most importantly, the human passion for understanding the universe have all continued to develop in the 50 years since Gene Cernan's footprints were left in the lunar dust. We are not starting from scratch. We are resuming a journey that was never fully abandoned, just temporarily rerouted. And here is something I find genuinely moving about this moment in history. The people who are working right now to return humans to the moon, the engineers at NASA, the teams at SpaceX and Blue Origin, the scientists studying those permanently shadowed craters full of water ice. Many of them grew up watching the Apollo missions on grainy television screens, or reading about them in books, or hearing stories from parents and grandparents who remembered watching Armstrong step onto the surface. The dream that those original missions planted in an entire generation never died. It got buried under budget cuts and political indifference and the grinding reality of keeping a space program alive in an environment that does not always value long-term thinking. But it never died. There is a woman named Gwynne Shotwell, the president and COO of SpaceX, who has spoken about watching the first space shuttle launch as a young girl and deciding, in that moment, that she wanted to work in aerospace. There are engineers at NASA's Johnson Space Center who chose their careers because of the Hubble Space Telescope images they saw as children. There are researchers at universities around the world studying lunar geology because of the samples brought back by the Apollo astronauts. The chain of inspiration that connects the first moon landing to the present day is real and unbroken. It runs through classrooms and libraries and late-night conversations under the stars and moments of pure, childlike wonder at the scale and mystery of the universe. That is not nothing, that is everything, but we are not done with our story yet, not even close. Because there is something about the moon, something physical, something tangible, something that sits in its geology and its history and its relationship to our own planet that we have not yet talked about, something that connects the very ancient past to the very near future in a way that I think will genuinely change how you see that silver light in the night sky. It has to do with what the moon is made of, what resources it holds, and what those resources could mean, not just for space exploration, but for the long-term future of human civilization on Earth itself. Because there is an element in the lunar regolith, embedded there by billions of years of solar wind, that some researchers believe could eventually change the way our entire civilization produces energy. It is called helium-3, and the story of what it is, where it comes from, and what it could do is one of the most fascinating and most consequential threads in this entire narrative. That is where we are headed next. If you're still watching, the universe has its hooks in you, and this channel was made exactly for that. Don't forget to subscribe and give this a like. Every video we go somewhere new and come back seeing a little more than we did before. Let's imagine something. It is sometime in the middle of this century. A cargo spacecraft lifts off from the lunar surface, carrying a payload of refined material extracted from the top few meters of lunar regolith. It docks with a transfer vehicle in lunar orbit. That vehicle begins the journey back to Earth. The cargo it carries is not gold. It is not diamonds. It is not any material that exists in abundance on our planet. It is roughly 1 metric ton of helium-3. And if the science behind it pans out the way some researchers believe it could, that 1 metric ton of helium-3 used as fuel in a fusion reactor could generate as much energy as burning approximately 40 million metric tons of coal. Let that number sit for a moment, 40 million metric tons of coal. From 1 ton of material, with no carbon dioxide emissions, no long-lived radioactive waste, no catastrophic meltdown risk, just energy, clean, dense, extraordinary amounts of it. This is not science fiction. It is not guaranteed science fact either. There are significant caveats we need to talk about, but it is a real scientific possibility, grounded in real physics, that a small but serious community of researchers and policymakers has been studying for decades. And it is one of the primary reasons that the moon is not just scientifically interesting or symbolically significant or geopolitically important. It may be economically essential. First, let us understand what helium-3 actually is. Helium is the second most abundant element in the universe. Most of it is helium-4, the ordinary kind, the stuff that makes balloons float, consisting of 2 protons and 2 neutrons in its nucleus. Helium-3 is a different isotope of the same element. It has 2 protons but only 1 neutron. It is extraordinarily rare on Earth, so rare that the entire global inventory of helium-3 is measured in tens of kilograms per year, produced mainly as a byproduct of the nuclear weapons program and worth roughly $30,000 per liter in its gaseous form. The reason helium-3 is rare on Earth, but relatively abundant on the moon, goes back to something we touched on earlier, the solar wind. The sun is constantly streaming particles outward in all directions, a continuous flow of charged particles, mostly protons and electrons, but also including helium nuclei of various kinds. This is the solar wind. At Earth, our magnetic field and atmosphere deflect and absorb almost all of it before it can reach the surface. The Moon has neither for 4.5 billion years. The solar wind has been blowing directly onto the lunar surface, embedding its particles into the top few meters of regolith. Among those particles is helium-3, produced in the Sun's fusion processes and carried outward with the solar wind. Over geological timescales, the Moon has accumulated an estimated 1 million metric tons of helium-3 in its regolith. 1 million metric tons of an isotope that cost $30,000 per liter on Earth, sitting in the top few meters of the lunar surface, waiting. Now here is where the fusion physics comes in. And I want to be honest with you about where the science stands, because this is an area where enthusiasm can sometimes outrun reality. Nuclear fusion, the process that powers the Sun, involves fusing light atomic nuclei together to release energy. The most commonly studied fusion reaction for energy production involves deuterium and tritium, two isotopes of hydrogen. This reaction releases a lot of energy, but it also produces high-energy neutrons, which cause the reactor materials to become radioactive over time and create a long-lived waste disposal problem. The helium-3 fusion reaction is different. Fusing helium-3 with deuterium produces helium-4 and a proton, and the reaction releases very few neutrons. In principle, this means a helium-3 fusion reactor would produce minimal radioactivity compared to deuterium-tritium fusion, and the neutron flux that damages reactor components would be dramatically lower. This is why helium-3 has attracted serious attention as a potential fusion fuel. It is not just energy-dense, it is potentially clean in a way that other fusion fuels are not. The catch, and it is a significant one, is that we do not yet have a working fusion reactor of any kind. Fusion energy has been 30 years away for about 60 years, as the joke goes. The engineering challenges of confining plasma at temperatures hotter than the core of the Sun for long enough to extract net energy are genuinely formidable. And helium-3 fusion is actually harder to achieve than deuterium-tritium fusion. It requires even higher temperatures and more precise plasma confinement. So the honest answer about helium-3 is this: if fusion energy is achieved, which is no longer the impossibility it once seemed, given recent advances, and if helium-3 fusion specifically proves practical, then the lunar regolith becomes the most valuable piece of real estate in the inner solar system. If fusion energy is not achieved, or if deuterium-tritium reactors prove sufficient without helium-3, then the equation changes significantly. But here is what I find remarkable about this. The question of whether to go to the Moon is no longer purely a question of exploration or science or national prestige. It has acquired an economic dimension that did not exist 50 years ago, not a speculative science fiction economic dimension, a real one, being studied by real economists, engineers, and policymakers in real institutions. And helium-3 is just the beginning of the conversation about lunar resources. Remember the water ice we talked about earlier, billions of tons of it, locked in those permanently shadowed craters near the poles. Beyond its value as rocket propellant, water is also a radiation shield. Hydrogen is one of the most effective materials for absorbing high-energy radiation, and water is approximately 11% hydrogen by mass. A water-filled shield surrounding a lunar habitat would dramatically reduce the radiation exposure of its inhabitants. Water, in the context of the Moon, is not just something you drink. It is structure, propellant, and radiation protection all at once. It is the oil of the lunar economy. And understanding how much of it exists, where exactly it is concentrated, and how accessible it is to extraction, that is one of the primary scientific objectives of the next phase of lunar exploration. Then there are the rare earth elements. The Moon's regolith contains significant concentrations of certain minerals that are economically valuable on Earth. Not necessarily in concentrations that would make lunar mining competitive with Earth-based sources under today's economics, but in a future where launching things from Earth is extremely expensive and where lunar industry is already established, the calculus could look very different. And then there is something even more fundamental, the Moon itself as a manufacturing base. The regolith contains the raw materials for making glass, for making certain types of structural materials, for making solar panels. A sufficiently advanced lunar presence could potentially be largely self-sufficient in terms of construction materials, building its own structures from local resources rather than shipping everything from Earth at enormous cost. This concept, using resources found in space to support activities in space, rather than depending entirely on Earth, has a formal name in the aerospace community. It is called in situ resource utilization, often abbreviated as ISRU, and it is not a futuristic concept. It is actively being developed and tested right now. The Perseverance rover on Mars carried an instrument called MOXIE, the Mars Oxygen in Situ Resource Utilization Experiment, which successfully extracted oxygen from the carbon dioxide in the Martian atmosphere. It produced oxygen in small quantities, but it proved the concept works. Similar technology, adapted for the lunar environment, could extract oxygen from lunar regolith, both for breathing and as a component of rocket propellant. The Moon is not just a destination, it is potentially a workshop, a supply depot, a place where the raw materials of a spacefaring civilization can be gathered and processed and put to use, reducing our dependence on Earth's gravity, well, for every single thing we want to put in space. But here is the part of the lunar resource story that most people find surprising when they first hear it. Nobody owns the Moon, not the United States, not China, not any private company. The Outer Space Treaty of 1967, signed by the United States, the Soviet Union, the United Kingdom, and eventually over 100 other nations, established the fundamental legal framework for activities in space. Its core principle is that outer space, including the Moon and other celestial bodies, is the province of all mankind. No nation can claim sovereignty over the Moon. It cannot be annexed, it cannot be colonized in the traditional political sense. This was an extraordinary legal achievement for its time, written at the height of the Cold War, when both superpowers had the capability to put weapons in space. The Outer Space Treaty prevented the militarization and nationalization of space in a way that could easily have led to catastrophic conflict. It deserves far more credit than it typically receives. But the treaty was written in 1967. It was written by people who could not have imagined commercial asteroid mining, private lunar landers, or the extraction of water ice from permanently shadowed craters, and it leaves a crucial question unanswered. If a nation cannot claim sovereignty over the Moon, can it, or its private citizens or companies, extract and own the resources found there? The United States took a position on this question in 2015 when Congress passed the Commercial Space Launch Competitiveness Act, which explicitly affirmed that American citizens have the right to own resources they extract from celestial bodies while stopping short of claiming territorial sovereignty. Luxembourg passed similar legislation. The UAE followed. Several other nations are developing their own frameworks. But China has not signed on to this interpretation. Russia has actively disputed it, and the international legal community is deeply divided on whether these national laws are consistent with the Outer Space Treaty. The result is a legal landscape that is, to put it politely, unresolved, and it is going to need to be resolved, one way or another, before any serious commercial exploitation of lunar resources can take place. Because no company is going to invest the billions of dollars required to establish a lunar mining operation without some clarity about whether the resources they extract are legally theirs. This legal uncertainty is part of a broader challenge that does not get enough attention in popular discussions of the return to the moon. Governance. Who makes the rules in space? Who resolves disputes? What happens if two competing lunar bases, one American, one Chinese, both want to extract water ice from the same shadowed crater? What happens if a private company's mining operation endangers a scientific site that another nation considers irreplaceable? What happens if a rocket launch from one country's lunar facility poses a risk to another's? These are not hypothetical questions for some distant future. They are questions that the next decade of lunar exploration is going to force us to confront. And the current international framework for answering them is, charitably speaking, inadequate. The Artemis Accords, a set of bilateral agreements developed by NASA starting in 2020, represent one attempt to address this gap. Countries that sign the accords agree to a set of principles for responsible lunar exploration: transparency, interoperability, the preservation of heritage sites like the Apollo landing locations, the deconfliction of operations to avoid harmful interference. As of early 2024, over 40 countries had signed. China and Russia have not. Instead, China and Russia have announced their own International Lunar Research Station project, a competing framework for lunar exploration with its own set of partner nations. The moon, it seems, is not just going to be the site of a scientific and commercial race. It is going to be the site of a governance race, a competition to establish whose rules and whose norms will define how humanity uses the resources of the solar system. The parallels to the early days of international maritime law or Antarctic governance are striking and somewhat sobering, because both of those frameworks, the laws governing the world's oceans and the Antarctica Treaty System, took decades of difficult negotiation to establish, and neither is perfect. The stakes in space are considerably higher. I want to step back from the geopolitics for a moment and bring this to something more personal, because I think it is easy, when discussing governance frameworks and resource economics and legal treaties, to lose sight of what is actually at stake here. What is at stake is the shape of the next chapter of human history. Think about what the world looked like before the age of ocean exploration, before European sailors crossed the Atlantic and the Pacific, before trade routes connected Asia to Europe to the Americas. The world was, in a very real sense, a collection of separate stories, civilizations that were largely unaware of each other, developing in parallel, occasionally intersecting, but never fully connected. The age of exploration changed all of that. It created the modern interconnected world, for better and for worse, with all the wonder and all the violence and all the complexity that entails. It opened up new possibilities and closed others. It redistributed power and resources in ways that shaped every subsequent century. The opening of space is the next version of that transformation. And like the age of ocean exploration, it will be shaped decisively by the choices made in its earliest decades. By the legal frameworks established, the norms embedded, the power structures formed, while the field is still young enough for those choices to matter. We are in those earliest decades right now. The decisions being made in the next 20 to 30 years about how humanity operates in space, who has access, under what rules, for whose benefit, will echo for centuries. That is not hyperbole. That is history, repeating its pattern on a larger stage. And here is what I want you to hold on to as we move toward the final chapters of this story. Every civilization that has ever looked up at the moon has seen something different in it. Ancient peoples saw a goddess, a god, a lantern hung by the divine to light the night. Poets saw longing and romance and the passage of time. Scientists saw a geological record, a gravitational partner, a laboratory for understanding the solar system. Engineers saw a destination. Economists are beginning to see a resource base. Strategists see a high ground. But underneath all of those frameworks, underneath the politics and the economics and the science and the law, the moon is something else, something older and more fundamental. It is a mirror, not literally, but in the sense that how we choose to approach it, whether we go back in a spirit of competition or cooperation, of exploitation or stewardship, of short-term thinking or genuine long-term vision, tells us exactly who we are as a species, whether we have learned anything from the patterns of our own history, whether the civilization that builds the next generation of lunar infrastructure is capable of thinking beyond the next election cycle, the next quarterly earnings report, the next news cycle. The moon has been watching us for 4.5 billion years. It watched the first single-celled organisms appear in Earth's ancient oceans. It watched the first animals crawl onto land. It watched the first human beings look up and wonder what that bright silver light in the sky actually was. It watched 12 people walk on its surface and come home, and it is watching now as we decide whether we are finally ready to go back. And this time, to stay. The moon has never stopped waiting. It hung in the sky above every civilization that rose and fell on this planet, above every war and every discovery and every moment of grace that humanity ever produced, patient and silent and indifferent to whether we ever found the courage to return. We went once, for the wrong reasons, and we walked away, but the universe does not grade us on our first attempts. It grades us on whether we learn, whether we grow, whether we eventually become the kind of species worthy of the cosmos we were born into. The technology is ready, the science is calling, the water ice is sitting in those frozen craters, undisturbed as it has been for billions of years, and somewhere right now, a child is looking up at that silver light in the night sky and feeling something they do not yet have words for. The same pull that every human being who has ever lived has felt when they looked up and wondered what was out there. That child may one day stand on the lunar surface, look back at the small blue world hanging in the black, and understand in their bones what Carl Sagan understood at a desk, what Edgar Mitchell understood in an instant, what 12 men understood when they left their footprints in the grey dust. That we are not separate from the universe, we are made of it, we are how it looks at itself. And the only brutal reason we have not been back to the moon is that we forgot for a while how extraordinary it is to be alive in a cosmos this vast and this beautiful, and how unforgivable it would be to stay home.